So, visualize this. You got two identical green carts that y'all have worked with quite often. Both tied to a string, both have a 50-gram mass suspended from the end of them. One cart has a 1 kilogram mass sitting on top of it. Okay? So one's your basic cart, the other one has a 1 kilogram mass sitting on top of it. Both have a 50-gram mass suspended from the end. I'm going to let go of it. They're both going to be allowed to travel for 2 seconds. Okay? Which one is going to have the greater change in momentum? The lighter cart, the bigger cart, or will it be the same?
Be the same.
Why?
Because the one with the bigger mass will be moving slower, but the one without the bigger mass will be moving faster. And then, so
Well, that's true. You're absolutely right. But how does that end up with the same change in momentum?
since
What are the two ways you can calculate change in momentum?
Mass and velocity.
Mass and change in velocity.
Yeah.
yeah,
And force time.
And force time.
oh yeah,
So if you were to draw
Oh, same amount of force, same amount of time. Because the
a
mass
force
on the-
time graph,
that's right.
would they both have the same amount of force acting on it?
Yes.
Mm-hmm.
Yes. So they're both going to have the same amount of force acting over the same amount of time. So what does the area underneath a force time graph give you?
The momentum.
Change in
in
momentum. Not momentum, change in momentum.
Change.
So is the area going to be the same for both of them?
Yeah.
Yes, so they're both going to undergo the same change in momentum. But which one's going to be going faster?
The one with less mass.
Yeah, so it's going to have a greater velocity to have the same momentum as the one that has more mass. Okay? Now, we're going to change it up. Same situation, same mass as 50 grams, that's 1 kilogram mass. But here's the difference. Now, instead of letting it roll for the same time, I'm going to let them both roll until they travel 0.2 meters. Now which one will undergo the greater change in momentum? The lighter cart, the more massive cart?
More massive cart.
Why?
Because the less massive car will undergo the same force for a shorter amount of time.
Talk about acceleration. Which one's going to have the greater acceleration?
The
The light
smaller
cart.
cart.
Smaller cart, right? True?
Yeah.
And distance traveled equals 1/2
AT squared.
AT squared. So the one that has squared, the one that is going to travel about 20 centimeters in so they're both going to travel the same distance. So the one that has the smaller time will have the greater acceleration, right?
Yep.
It's going to speed up faster. So the less massive one is going to take less time, so it's going to be the same force, but that's going to be over less time. Therefore, you get the one with the smaller mass will have less change in momentum. The other one's going to have a greater change in momentum. I promise you, there's going to be situations where you're going to have like two carts. They're going to run into each other, right? So how do all linear momentum problems start? What do you write down? Sum of, oh, it's going to be long. Now, here's what's scary, is that, and I've seen this happen disturbingly large numbers of times, is that the momentum test average is actually worse than the planetary motion test average. Because you sit there and go, it's just momentum, it's not that tough. And then you get your omegas handed to you because you didn't study. Okay? So
I'm gonna do that one.
you think, oh, it's not that tough, I don't need to study, and then and because you think, oh, the planetary motion is so tough, cube roots and all this good stuff, right? And it's just momentum, and then you go, oh my God, that's not good. So it has been known to happen, not all the time, just saying it's been known to happen. So how about the momentum of 1 plus the momentum of 2 equals a new momentum of 1 plus the new momentum of 2, right? So they all start, true? Now, if they stick together, what can you do over on this side?
Oh.
If it's a California problem,
It's the same.
factor out,
The mass.
how about factor out the velocity?
Velocity. Yeah. Well, the masses do their adding thing, and yeah.
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 Okay.
You know what I meant.
They do the thing.
Now, you have two situations. One where the carts hit and they move off together, okay, California problem. The other situation where here's cart 1, it's at rest. Cart 1 hits it and bounces back. So situation number 1, this cart moves in, they hit, they move off together. Situation number 2, you have one at rest, the other one comes in, hits it, and it bounces back. In which situation is there going to be a greater change in momentum of the system? Where they hit and they move off together, or one hits and bounces back?
Hits and bounces back.
Hit and bounce. Every time you hit and bounce, that's a greater change in momentum because your velocity has to go from like positive to 0 to negative. So whenever something hits and bounces back, that's a greater change in momentum. Now, this is where this can play out. So let's say that you have a thin rod that can pivot about a point.
Okay.
Situation number 1, a chunk of clay comes in, it hits it, the clay hits, it stops, and then the rod moves off.
Yep.
Situation number 2, same rod, but now it's a bouncy ball, it's going to hit and it's going to bounce. Which one will make the rod undergo the greater change in momentum?
Bouncy ball.
Bouncy ball will, right? Absolutely. Now, you know the V equals R omega, right? And you know D equals R theta and A equals R alpha. True? Got all that. So, if you look at momentum equaling mass times velocity, could I put in R omega into here?
Yeah.
So could I write that as M times R omega?
Yep.
True?
Mm-hmm.
Okay. Now, let's look at a planet moving in an elliptical orbit. Okay? Now, stay with me here. Stay with me. Stay with me. So, what do you know happens when it gets closer?
It goes faster.
Faster speed.
So you have a smaller omega, or a smaller radius, but then you'd have a
Big
greater,
Oh my god.
Small R, big butt.
yes. Out here,
Small
you have
butt,
what?
big radius, small butt.
Big radius
Big R, small butt.
Small butt.
and
Butt,
a
butt. Little butt.
small butt. Because guess what? Momentum has to be conserved. Now, L equals I omega. As the Earth goes around the orbit, is omega going to change?
Yeah.
Excuse me, is I going to change?
No.
No. Okay? That's not going to change in terms of the mass. But that's going to be mr squared, right?
Yeah.
Mass isn't going to change. Is the radius of that orbit going to change?
Yes.
Mm-hmm.
Oh.
So angular momentum has to be conserved. So this is why it has to move slower when it's further away and has to move, so it's just like the spinning object. It's the same idea. Because angular momentum and linear momentum have to be conserved.
Are we gonna have a question like that on the test?
Very real possibility, or at least the concept of it. Okay? On the assignment that I just gave back,
Size of where does the planet fly off?
you had the spinning ball, right? Where the
Triple
bug
size,
comes and
too.
lands on the ball. I promise you, you're gonna have a question like that. Okay? Promise you. There's a question like it on the review. Okay? But it's the same thing. L1 plus L2 has to equal L prime 1 plus L prime 2. Guess what? The angular momentum still have to add up to 0. Now, since it lands and sticks, what can you do over here?
California.
Yes, it's like a California problem. So you can factor out the i's and search for butt prime. Okay? Promise you. Yes,
Why is this one way more useful than ours?
because that's the honors one and that's the AP one.
But this one kind of sucks, and this one's super useful.
But if you take the AP test, that's the equation sheet that you're gonna have.
Is anyone taking the AP test?
Yes.
No.
So how about Gapshawn uses this one and the rest of us use this one?
The rest of us
It's a
get the
hand
big
you
dog
dealt.
equations.
Huh?
It's the hand you're dealt. Now,
Well, this hand's good and this one's bad.
sorry.
And this one's readily available. And I would like to change hands.
I'm gonna photocopy that and
No.
keep it.
Oh, this one's so much better.
Let me see.
It's literally all of the equations. Instead of trying to like derive them from this
Like 4 pi squared r over t squared.
Yeah. So trying to like derive them from this rotistic looking thing as they're handed out in the form that you want them.
This is very nice.
Isn't it? It's got the stuff from linear to all of it.
Yeah. Sorry.
It's got fluid mechanics and thermal physics on the back.
Which you guys will have as well. Okay.
I assume that.
I promise you there's gonna be a problem where the ball hits and it bounces back. Okay, that big problem that we worked out.
Make sure to do the full swing and velocity.
What's the only thing I can change on that problem?
The numbers.
Yeah, I can change out how high it is when it falls, how high it bounces, how long it's in contact with the ground, and the mass. That's it. It's the only thing I can change. And yes, you're gonna have to draw a velocity time graph for it. What's the velocity time graph gonna look like? Start at 0,
And then it's going to accelerate downward.
Boom.
at
Boom. Boom. 9.8.
9.8
negative
meters per
9.8
second.
meters per second squared. It's gonna hit the
Zigzag.
ground.
It's going to accelerate really quickly. Upward.
And it's gonna go woo.
And then it's gonna go like this. Are these two lines gonna be parallel?
Yes.
Yeah.
Yes, because it's the only force acting on it.
Gravity.
Gravity.
So gravity is a force.
So what do you know about this negative velocity relative to that positive velocity?
What?
What do you know about the negative velocity that it has when it lands relative to the positive velocity it has when it takes
Well,
off?
it'll be moving faster when it hits the ground than
Yeah,
when
so
it-
this negative velocity here has to be bigger than that positive velocity when it takes off.
We
If
thought
they were the same, what would happen?
it bounced back to the same height.
Yes.
We thought you were about to
It
pull
would
up
do it
some like
forever.
magical relation that we never remembered.
No.
What?
No. No.
What?
Huh?
You think I'm gonna be able to ask you to find the acceleration in each segment?
Yeah.
Yes.
Yes.
Mm-hmm.
And you know the change in momentum equals
Oh, right, 'cause he's gonna
force
do the
times
whole
time. Okay? Promise you that.
Nice on delta V.
What does the slope of a momentum time graph give you? Why?
Momentum is.
What's momentum in?
Oh, FT.
Newton seconds?
That's right.
Time in?
Seconds.
Seconds.
Divide Newton seconds
Divide
by seconds.
Seconds.
Oh,
Check my math, you get.
Newtons.
If I gave you a sloping line on a momentum time graph, what does that indicate?
The force
Force.
is changing.
No.
It's different.
There's a force being applied.
Did
There
you
is a
just really
force.
say it's different?
Yes.
I hate you.
Don't worry, Berg. I hate me too.
Bad.
Bad and dumb.
Absolutely. With capitals.
Cohen is a bad boy, all caps.
Oh.
Cohen, what did we just say the slope of that graph represented?
Force?
Is the slope changing?
Yeah.
Love of God, is the slope changing?
No, it's, my brain was like, it's not horizontal. Yeah, it's changing.
Bad.
If the slope is the same, is the force the same?
Yes.
If the force is the same, the acceleration is the same.
Unless the mass is changing.
Which is not.
Thank goodness.
We'll deal with
That would be
later.
weird.
What does the area underneath a momentum time graph give you?
Newton seconds.
Newton
squared.
seconds squared.
Which
Nothing.
represents what?
Newton meters.
Nothing.
Nothing.
Hold on, let me think about
The
it.
area underneath a momentum time graph has no meaning. Now,
It's the end, guy.
what if it was a force time graph?
Then
That
that's
would be changing momentum, because the
Yeah.
units here would be
Newton seconds.
Newton
Second.
seconds. If I gave you a force time graph that looked like this, what can you find at that peak?
F max.
F max, okay? Is it still true though, does the area underneath this force time graph still represent change in momentum?
Yes.
Yes.
Yes. Now, what if I gave you a force time graph that looks something like this?
Well, that's cringe and dumb. And you would never do that because you're nice.
It's funny.
That's funny. That's funny, Cohen.
He's about to make the first time graph do a loop-de-loop.
Roughly. What's that area up above going to be? A positive or negative number?
Positive.
Positive.
Relatively big, relatively small.
Relatively big.
Relatively big positive number.
Nice.
Compared to this area down below, which would be a
Relatively
Negative.
small negative
relatively
number.
small negative number.
And you just add them together.
Oh! And that would get you the overall net
Net. Change momentum.
Change
change in momentum.
I almost said displacement and then shot myself.
Now, change in momentum
would've
also
beat you if you
equals
said
what?
M delta
Mass
V.
times.
Change in velocity.
So if you knew the mass of the object and you can find the overall net change in momentum, you could find the.
Change in velocity.
Now, how could that physically play out when you're driving?
You hit a child. I don't know. That's just-
Let's say you're moving with a positive velocity, right? So maybe at this point you're applying the gas, okay? Because you have a positive change in momentum. If you're defining your velocity as being positive, so what are you doing in the top part of the graph?
accelerating. Positively.
True. Are you speeding up or slowing down?
Going faster.
You're going faster. Now, when that line begins to slope, what did you do?
Hit the
You
brakes.
decreased the
brakes.
amount of positive force. What did you do?
Saw a child. Braked.
Well, you took your foot off the gas,
Yeah.
right?
Uh-huh.
Because you decreased the amount of positive force. Then, what did you do?
Brakes.
Yeah, then you hit the brakes as hard as you had hit the gas pedal?
No.
No.
No, why?
Because this.
Forces aren't the same.
Yeah.
They're different.
The slope is steeper.
Look at the amount of force.
It goes to 0.
It's less!
Yay!
This is gonna be a very bad test.
Let me hand out the stuff.
The retake is gonna be. Dude, is everybody ready for a retake? We should all just come in like one day together and take a retake.
Yeah.
We should. We should come in tomorrow for the retake.
You just want to go straight to the retake?
Straight to the retake. We
No,
already
we
know
don't
it's
want
gonna
the
be
test.
bad.
We just want to go straight to the retake.
Straight to the retake. We already know
we'll
the
call
test
it
is gonna
test
be
of D
bad.
and be done with it. Why is he skating like that?
Are we gonna
Bro's
have
sticking his
like,
butt
weird,
out.
like this angle with like a rod in between and calculate like the angular momentum of that rod? Okay, because I got that one wrong and I still don't understand how to do it.
Okay,
Let's give up.
so if push comes to shove, and you're short on time. On number 15, this is where you have a sphere with a piece of clay landing on it, and you're asked to find the new angular velocity. Okay? On 14, that's where you have the bouncing ball problem. Okay? So if push comes to shove and you're stressed for time, make sure you do 14 and 15. Okay? That was going to be kind of the big problems on the test. I'm not saying the other ones aren't important,
time now.
but if you're running short on time,
Worst. I have
make
so
sure that
much
you
time
can do
now.
14 and 15. So, all right, I've endured enough pain and punishment. Now, keep it going though. Tomorrow, I'm going to be here, but I've got to leave. I've got to leave a little bit early because it's a long story. I got to go over to one of the elementary schools. This is Kansas Teacher of the Year thing, so I got to go over there to one of the other schools. So I'll probably leave about 10 till 9. Mr. Woodruff's going to be in here to watch it get done. So I'll be here, but I'm going to leave a little bit early. So if you all want to come in, get a head start, I'll be here. That's cool. Okay, so that's all up to you. So if you want to make sure, like, oh, my chi will be out of focus if Burkamp leaves. I need to get down while Burkamp is still in the room. So just know that I'm going to leave a little bit early. Okay, now you can shut it down.
I'm gonna take the
Need to